We have identified the disadvantages of non-overlapping subcarriers, and we understood that the bandwidth requirement of such a technique where we have non-overlapping subcarriers is very large. And so we are thinking of methods by which we are able to perform this multi-carrier transmission by using overlapping subcarriers. Okay, we want overlapping subcarriers whose bandwidths overlap with each other, and we want to have we are trying to make such a transmission so that the bandwidth requirement is less when compared to the multi-carrier technique where we are using non-overlapping subcarriers. And this is primarily to improve the spectral efficiency. And yeah, you can clearly see here the bandwidth requirement is less when compared to the multi-carrier technique where we have non-overlapping subcarriers. And so we have identified a set of subcarriers. Okay, we have identified a set of subcarriers that is cos of 2 pi f naught 2 pi into f naught plus I divided by Tn into T, where I is equal to 0, 1, 2, etc., etc. It goes up. I takes integer numbers 0, 1, 2, etc. So these are a set of subcarriers where I goes from 0, I sometimes is equal to 1, 2, etc., etc. I takes integer values, and you can see this is nothing but the frequency. It is the frequency of the subcarrier. It is a frequency of the subcarrier, and we have seen this before. We have seen similar expressions before for multi-carrier technique. And what is f naught? F naught is, please refer to my previous classes. F naught is the sender frequency of the first subcarrier. F naught is the sender frequency of the first subcarrier. F naught is the sender frequency of the first subcarrier, and we will see, we'll prove that these set of subcarriers, they form an orthogonal set. Okay, we'll prove that this is a set of subcarriers which contain subcarriers with frequencies f naught plus 1 by t and f naught plus 2 by t, and etc., etc. So we'll see that if you have these subcarriers, they form an orthogonal basis function. They form these subcarriers form orthogonal basis functions. Okay, these set of subcarriers, they form an orthogonal basis functions on the interval. Now that is very important. Which interval you want it to be? On the interval 0, tn, 0, tn. In some textbooks, you can see a phase offset of subcarrier also coming to picture, but I have neglected, for convenience, I have neglected the subcarrier offset, assuming that the subcarrier offset is 0 in this case. Okay, now we'll try to prove this point we'll try to prove this, that these set of subcarriers form an orthogonal basis function in this interval 0, tn. So in order to prove that, if they are orthogonal, then we'll try to solve this equation 1 divided by tn integral 0 to tn cos 2 pi f naught plus I by tn into t. Okay, this is one of the subcarrier having the frequency f naught plus I divided by tn into this is the frequency part, f naught plus I divided by tn, and you have another subcarrier cos 2 pi f naught plus j divided by tn into t dt. Okay, we are trying to solve this basically multiplying two different subcarriers, and if they are orthogonal over this interval 0 to tn, if they are orthogonal, then your result must be 0. We'll see what the result is. And this I and j, they are two integers, two integer numbers, and we apply this formula cos a into cos b. Cos a into cos b, it is equal to 1 divided by 2 into cos a plus b plus cos a minus b. Okay, we'll try to apply this formula here. So you have 1 divided by 2 tn integral 0 to tn. First term is cos, let me put a bracket here. First term is cos a plus b, and so you will have cos of 2 pi into 2 f naught plus I plus j divided by tn into t. So that is the first integral dt. And you have the second part, cos a minus b, having this equation integral 0 to tn two pi into I minus j divided by tn into t dt. I'm sorry. Should be a cos of 2 pi into I minus j t divided by tn into dt. Okay, the bracket is closing here. So what happens is when you add these two, you have 2 pi into f naught plus f naught is 2 f naught, and you have I plus j divided by tn, and when you subtract, you have f naught and f naught getting cancelled, and the remaining part is 2 pi into I minus j divided by tn. And so you have these two expressions here, and we'll see what happens to the values of these expressions. So consider this equation, this part. What happens is that, what is the frequency of this? What is the frequency of this wave? We are trying to see whether this function is orthogonal in the range of 0 to tn. We are trying to see whether they are orthogonal in this range 0 to tn. And what is going to be the frequency here? Here the frequency is, if I take the LCM and add these two f naught plus I plus j divided by Tn, these two terms, if I add, then in the numerator I will have this term 2 f naught into Tn plus I plus j divided by Tn. Of course, you will have this, and you can see that f naught Tn is a value which is much greater than 1. Okay, why is it like that? Because f naught, remember, f naught is the first central frequency of the center frequency of the first subcarrier. So it is a large value. F naught is a large value. Okay, and what is Tn? Tn is the time duration, this time duration. So f naught Tn becomes a large value when compared to Tn. Okay, f naught Tn becomes a large value when compared to Tn. And what happens to the frequency of this wave? The frequency of this wave becomes very large. All right. So, like an example, I will show you. If the wave was like this, okay, if I had a wave like this, the frequency, what is the frequency of this wave? You can very well see the time period is Tn, so the frequency is going to be 1 divided by Tn. Okay, but here what is going to be the frequency? The frequency is going to be a very large number. It is f naught 2 into f naught Tn plus I plus j divided by Tn. So you have this multiple multiplied with 1 by Tn. So your frequency is going to be a frequency of the wave is going to be a very large number, and as such your wave will look something like this. They will be very closely spaced waves like this, subcarriers, very closely spaced, and there will be a large number of subcarriers from 0 to Tn, and if you integrate, if you do this integration 0 to Tn in this time range, the answer you are going to get is 0, because you will have equal number of positive areas as well as negative areas. So your this integral will have a value of 0. Okay, that integral will have a value of 0, because f naught is a large value, and f naught is typically in megahertz range, and when you multiply with Tn, the time duration, and that's going to be a very large value when compared to 1, and you will have a high frequency, and this high frequency when integrated from 0 to Tn will have integrated to 0, because you have equal positive areas as well as negative areas. And we'll see what happens to this this particular integral. So now what's remaining is this. It is equal to 1 divided by 2 Tn integral 0 to Tn cos of 2 pi I minus j divided by Tn into t dt. Now you can see that the frequency now is I minus j. So standard form is cos 2 pi ft, right? So now the frequency is I minus j divided by Tn, and this I minus j, what is I minus j? Both are integers. I and j, they are integers. If they are equal to some non-zero value, okay, if I and j, if they are equal to some non-zero value, then you will have this 1 by Tn multiplied with some value, right? For example, now I am we are looking at this range from 0 to Tn. We are looking at this time range 0 to Tn. And this, if I had just one wave like this, if I have a wave like this, the frequency is 1 by Tn. If I have a wave, if I want to have a wave with frequency 2 divided by Tn, which means twice the along this range, you need to have a wave like this. Okay, so the frequency of this wave is 2 divided by Tn. Okay, it is twice that of the other wave. Right, it is twice that of the wave having a frequency of 1 by 2n. What if it is 3 by 2n? You will have 3 cycles. You will have 3 cycles in this range 0 to Tn. So whatever the cases, you will have equal positive and negative half cycles. So in the first case, you can see when you have a wave uh, which is having a frequency of 1 divided by Tn, you have equal positive and negative areas. When you have a wave which is having a frequency 2 divided by Tn, again you have equal positive and negative areas. And whatever be the multiple, this I minus j divided by Tn, if I minus j is not equal to 0, then your answer is going to be 0. You will have some multiple value here. Other than 0, you will have some multiple value, and your answer is going to be 0. So the answer to this integral is, it can come in two ways. One way is that it could be 0 for I not equal to j, and the other answer you can have is when I is equal to j. When I is equal to j, what happens? You have 0 here, and cos 0 is 1. So you have, let me simplify it here, 1 divided by 2n integral 0 to Tn dt. So you have cos 0 equal to 1. So you have this, and what is this? This is equal to 0.5, right? So 0.5 or 1 by 2 when I is equal to j. Okay, this is a very important result. This is a result of integrating two expressions, two subcarriers, cos 2 pi fit and cos 2 pi fjt dt from the interval 0 to Tn, 1 by Tn. So when I do this integration, if fi is f naught plus I divided by Tn, and fj is f naught plus j divided by Tn, and if fi is equal to fj, then you have some value, which means only if they are same, only if these subcarriers are having the same frequency, you will have some value 0.5. But when these subcarriers are different, okay, when these subcarriers they are having a separation of some value of 1 by Tn, then you will have 0 value. If I is not equal to j, if these frequencies are not equal, then you will have 0 value. And what is the least difference that you can have here? What is the least value of multiple that you can have here? It is I minus j equal to 1. So one possibility is I and j are the same. In that case, you have 0 value. The other possibility, the smallest multiple, the non-zero multiple that you can have is I minus j is equal to 1. And as such, you can see that that is the smallest separation you can have between two subcarriers. So this indicates this result, that is only when they are the same you will have the value 0.5, when they are different, when the frequencies are different, you have the value 0, and this result, it indicates that these subcarriers are orthogonal. They are orthogonal with a orthogonal on the time interval 0 to tn. They are orthogonal in the time interval 0 to tn, and also the least value of frequency separation between them to be orthogonal is 1 divided by Tn. That happens when I minus j is equal to 1. Okay, this happens when I minus j is equal to 1. You can see when I minus j is equal to 1, you have cos 2 by tn into t, and of course that will integrate to 0. That is the least frequency separation value that you can have. So when you have subcarriers which are overlapping in nature, okay, these are subcarriers which are overlapping in nature, okay, etc. They are overlapping in nature. The center frequency is f0, f1, f2, etc. fn minus 1 with a bandwidth of each subcarrier. The bandwidth is bn, which is equal to 1 by tn. The least frequency separation, okay, the frequency separation here, the separation between two frequencies. The least value of frequency separation is bn, which is equal to 1 by tn. It is equal to 1 by tn. So f1 is equal to f0 plus 1 divided by tn, and you can have multiples, f0 plus 2 divided by tn, etc. And f2 is f0 plus 2 divided by tn, etc. And what you have to notice, these subcarriers, they are overlapping, but these subcarriers, they are orthogonal to each other. Being orthogonal means that you are able to separate it at the receiver. You are able to separate each one of them by multiplying the corresponding frequency. So that is a speciality of orthogonality of subcarriers. Okay, and what we have proved right now is a set of subcarriers which are having a bandwidth of 1 divided by tn. They are orthogonal in the range 0 to tn, with the least frequency separation between consecutive subcarriers. And the frequency separation should be at least 1 divided by tn, which is equal to their bandwidth itself. Okay. So all this leads to the idea of OFDM. So we haven't reached OFDM yet, but all these ideas definitely will lead to the idea of OFDM. Okay. Now, when you have now, what is the total frequency requirement? Total frequency requirement for this transmission. We'll see that. If I have subcarriers, remember I'm drawing the frequency axis. I have subcarriers which are overlapping in nature, like this. Sorry. The idea when you draw this means it is when you have this subcarrier, the other subcarrier should start from here, and when you take this subcarrier, the other subcarrier should start from here. So that you sample at one point, you will have only that subcarrier, or all the other subcarriers will have zero value. If I sample at this point, then you will have only this subcarrier, and all the other subcarriers will have the value 0. The idea it goes like that. And you can have n number of subcarriers. Here also there is this roll-off factor beta. There is time limiting function epsilon. So this pulse definitely has this. It has 1 by Tn plus beta by Tn plus epsilon by Tn, which is 1 plus beta plus epsilon divided by Tn. So the pulse definitely has this bandwidth, but the advantage here is that the subcarriers are overlapping with each other. So you need only a frequency separation of 1 divided by Tn here. You need only a frequency separation of 1 divided by Tn here. This frequency separation is 1 divided by Tn. Again, this frequency separation, it is 1 divided by Tn. And you will have this effect of roll-off factor and time windowing factor epsilon on these two pulses, on the first subcarrier and the last subcarrier. For the first and the last subcarrier, will have this effect of beta and epsilon, and as such the bandwidth required when subcarriers are overlapping, the bandwidth requirement is 1 plus I'm sorry, you will have 1 by Tn. How much you will have? You will have up to the uh, nth subcarrier. You will have this 1 divided by Tn, or you will have n plus beta plus epsilon divided by Tn. Okay, so you will have n times the Tn, and then you have these factors beta and epsilon, which are of course the contributions of the first and the last subcarrier. Okay, right. So the bandwidth requirement is less when compared to the case where the subcarriers are overlapping with each other. Another question is how to, yeah, one more. In some, most of the cases, you can approximate this as n divided by Tn. That is because usually n is a large value when compared to beta and epsilon. So in some of the textbooks, you can see this approximation approximated to n divided by Tn. Now the question is how to separate out these overlapping subcarriers. So how do you separate out these overlapping subcarriers? So these subcarriers are overlapping with each other. In time domain, the waves, these subcarriers, they get added with one another. How do you separate out it? Okay. The process is very similar to what you may have seen in BFSK and all. You multiply with the corresponding subcarrier frequency itself. Like that, you're able to get back the original signal. So let me just go back to the previous diagram where we had uh, non-overlapping subcarriers. You have here this is a diagram of the transmitter side of the case where subcarriers were non-overlapping. So you can use the same diagram for overlapping subcarriers also. Only thing is the frequencies have now getting shifted. We have adjusted in such a way that the separation between the frequencies is 1 divided by T and the subcarriers are overlapping. And what is S of T? So I want to find an expression for S of T. S of T is basically summation of all these signals, S0 of T, S1 of T up to Sn minus 1 of T. I can write it as summation J is equal to 0 to n minus 1 Sj of T cos 2 pi Fj into T. So basically a summation of all this S0 of T into cos 2 pi F0 T, S1 of T into cos 2 pi F1 T, Sn minus 1 of T into cos 2 pi Fn minus 1 T, and add all these things and you have this value of S of T. So this is your S of T, and J is a variable that I have used for this summation value. And this signal is coming towards the receiver side. It is coming towards the receiver side. And how can you separate it out? How can you separate out each of these? I want to separate out S0 of T, S1 of T up to Sn minus 1 of T. How it is possible? From this summation of all these subcarriers, how it is possible to separate out one particular subcarrier? The idea, let us see how we can work it out. So at the receiver side, now we are not considering the effect of noise. Okay? We are not considering the effect of noise now. Effect of noise for simplicity. We are also not considering the effect of channel. Okay, let's say that this signal directly goes to the receiver. We'll see what happens. What happens is the receiver does this operation 0 to Tn. The signal S of T reaches here. S of T will get multiplied by cos 2 pi F it dt. Okay, and let me expand S of T here. That is integral 0 to Tn. S of T is summation J equal to 0 to n minus 1 S j of t cos of 2 pi f j t into cos of 2 pi f I t dt. And I can interchange summation and integration because they are linear operations. Second, j equal to 0 to n minus 1 integral 0 to tn s j of t into cos of 2 pi fjt cos of 2 pi fit dt. And from the previous analysis that we did for the subcarriers, proving that they are orthogonal to each other, okay, this is I. Please don't confuse, this is I. Okay, from that analysis we know that this result equal to a non-zero value only if I is equal to j, otherwise it is 0. Okay, so this result, this is equal to 0 if fi not equal to fj and it is equal to 1 by 2 if fi equal to fj. Okay, it is having some 1 by 2 or some non-zero value only if fi is equal to fj, and you will get so we'll neglect the case when it is 0. When remember this operation happens at one of the communication chains of the receiver. Okay, I'll show you the receiver soon. This happens at one of the communication chains where the incoming signal, this is the incoming signal, it is multiplied with cos 2 pi fit dt, and this gives the value summation j equal to 0 to n minus 1 integral 0 to tn only if, okay, this gives the value uh, some non-zero value only if this frequency fi is equal to fj, or in other words only if I is equal to j, or in other words you can say it is si of t dt. Okay, because only when I is equal to j this has a non-zero value, right? And so this summation uh, is cancelled off because this works for only one value I is equal to j, and for all the other frequencies, all the other subcarrier frequencies, this result is 0. Only for I is equal to j you will have the symbol, so this is equal to si. Okay, basically what has happened here is the incoming signal, which is a composite signal which is having a number of subcarriers, when it get multiplied by cos 2 pi fit, the ith symbol in this set, okay, ith symbol in this set, it has come out here, and with this idea we are able to design the receiver of overlapping subcarrier multicarrier transmission. And so this is the diagram for a receiver of overlapping subcarrier. It is a diagram for a receiver of overlapping receiver structure for overlapping subcarriers. Receiver structure for overlapping subcarriers. And you can see here the symbol s of t, which is a composite symbol having all the symbols, addition of all the symbols, sj of t cos 2 pi fjt, uh, when it gets multiplied by cos 2 pi f naught t, the first symbol s naught of t comes out here. So s naught, a cap is given because it is an estimate. S naught cap is the estimate of the symbol s naught, and when it gets multiplied by this frequency cos 2 by f1 t, the symbol s1 comes out. And from this composite signal, which is an addition of all the symbols s naught s1 up to sn minus 1, we are able to multiply this s of t with the corresponding subcarrier frequency, and uh, we are able to extract that particular symbol that you need here. And you have a symbol demapper here which does the demodulation, and finally you have the subcarrier stream, which is having a data rate of r divided by n bits per second. All these are combined to give uh, a effective data rate of r bits per second. Now a question might be, what if the channel noise and the channel coefficients are also considered? So in the analysis which we did before, we didn't consider the channel noise or the effect of channel coefficient. So if that is also considered, let us see what the equation is going to be. So when the effect of channel noise and channel coefficient are considered when the effect of channel noise and channel coefficients are considered, then you have subcarriers like this which are overlapping in nature. You will have the channel response, something that goes like this, and the value of channel coefficient at this point, say it is alpha I. The value of channel coefficient at this point, this is f naught, so I will write it as alpha naught. The value of channel coefficient at this point, f1, alpha I, alpha 1, at this point alpha 2, etc, etc. So these are basically sampling points. When I sample at this point, you can see that I only have the effect of this particular subcarrier. All the other subcarriers are 0. And if I sample at this point, I will have the effect of only this subcarrier. All the other subcarriers are 0. And if I sample at this point, so we need to draw this diagram of overlapping subcarriers in such a way that we are able to minimize or make the effect of all the other subcarriers 0 when the sampling of a particular subcarrier is done. When I consider this channel noise and channel coefficient into picture, SI cap here, this symbol, these symbols S0 cap, S1 cap, etc., the estimates will have the values of symbols multiplied with this channel coefficients. So here S0, which is the first symbol corresponding to the first subcarrier, S0 cap will have alpha naught into S0 plus N0. Okay, S1 cap will have alpha 1 S1 plus N1. So each of these symbol estimates, they have the values alpha naught s naught plus n naught, where this is your channel coefficient at that point. It is basically the frequency response value at f naught. Okay, this is the frequency response value at f1, etc. So this is the effect of channel coefficient. This is the effect of channel noise. So noise simply gets added, and it is additive white Gaussian noise, AWGN, and the noise value simply gets added to the symbol. Now you can see why S0, S1, all these are written as estimates. You have this cap here which shows that it is an estimate. We are not actually getting S0 here. Okay, we are getting alpha naught S0 plus N naught, and we are thinking of ways how can we extract S0 out of this. So you have at the receiver, you have alpha naught S0 plus N0. You have alpha 1 S1 plus N1, and we are thinking of ways how can we extract S0 out of this expression. So you want to cancel this channel coefficient effect, and you have many detection techniques. Okay, many detection techniques in order to extract S0 out of this whole mixture, this whole addition value. So there is a multiplication, there is a complex multiplication with the channel coefficient, and also there is addition of noise. And we have many methods where we are able to detect the symbols out of this particular addition mixture. So you have sometimes you have zero forcing receiver, you can have MMSC receiver. There are other receivers like LS, least squares receiver, maximum likelihood receiver, and many techniques we can have. Okay, so with that I'll end the class for today.